Welcome. We will start the ARISE webinar in 1 minute. Well, welcome everyone, and thanks for joining our last ARISE seminar. I am Anna Capuano, Professor of Biostatistics in the Department of Neurology and Public Health Science of the University of Chicago. ARISE is an educational program of the American Statistical Association, SDSA, that I have the honor to serve as educational officer. Our first speaker is Jianshen Chen, PhD candidate of biostatistics at Boston University, advised by Professor Catherine Luneta. Jianshen will present a proteomic signature of the pace of frailty, 112 protein score derived from the Framingham offspring data and harmonized with Olink assays in Framingham Gen3 and the UK Biobank. Next, we will hear from Alessandra Pessina, Research Assistant at Aging Research Center of the Karolinska Institute in Sweden. She holds a master in mathematical engineering from Politecnico di Milano, Italy, and advised by Dr. Katerina Gregori. Alessandra introduced multiple imputation for panel data for multi-stage illness DAF models, pragmatic solution when patient assessments are infrequent and transition times are unknown, as in many dementia studies. We will close with Dr. Deependra Thapa, postdoctoral research fellow at Indiana University School, advised by Professor David Ellison. He will tackle a foundational question: do life-extending interventions compress morbidity or simply extend life with illness? Each talk will be 15 minutes, followed by a brief Q&A. So with that, Jianshen, the floor is yours.
Let me share my slides. You can see in the presentation mode, right? Okay. Good morning, everyone, and thank you to the ARISE program for inviting me today. My name is Jianshen Chen, and I am a PhD candidate in biostatistics at Boston University School of Public Health. Today, I will present our recent work on developing a proteomic signature of frailty pace, a biomarker that reflects biological aging and predicts disease and mortality. So for the physical frailty that we will refer to as frailty hereafter is a syndrome of physiological decline and high vulnerability to adverse health outcomes in older adults. And here we will follow the frailty phenotype, which defines the frailty based on 5 components: the unintentional weight loss, exhaustion, weakness, slowness, and low physical activity. And as these symptoms accumulate, individuals will progress from the non-frail to pre-frail and eventually to the frail status. And biological aging is not simply about counting the years. It is influenced by a wide range of molecular and cellular processes, including those shown in the figure, markers of biological aging. And these processes collectively shape an individual's biological age, which may differ substantially from their chronological age. And over the past decade, researchers have developed a variety of aging clocks to quantify the biological age using molecular data such as the DNA methylation, metabolites, and proteins. While the epigenetic clocks have been highly influential, their molecular results often show weak concordance with the downstream gene expression and protein levels, making the mechanistic interpretation challenging. And compared with the limitations of epigenetic clocks, proteins lie closer to the functional endpoints of biology. And many plasma proteins are directly linked to the hallmarks of aging, such as inflammation, metabolic dysregulation, and loss of proteostasis. And recent high throughput technologies such as the Olink and the SomaScan have made it possible to measure thousands of proteins across large cohorts, giving us unprecedented opportunities to characterize the biology of aging. Most existing proteomic aging clocks focus on static endpoints like the chronological age and the mortality risk, not on the aging phenotypes. And several cross-sectional studies have shown that proteomic profiles are linked to age-related phenotypes, including frailty, and identifying proteomic correlates of frailty that reflect muscle weakness, slowness, and inflammation. These findings suggest that proteomic changes will reflect the aspects of the physical decline, but they mainly provide the snapshots rather than trajectories. However, as we know, aging is a process, not a snapshot. So we ask the question, can we develop a proteomic signature that captures the pace of frailty progression, which reflects biological aging and predicts downstream outcomes? And our goal of this study was to develop and validate a proteomic frailty pace signature that reflects longitudinal changes in physical function and test whether it predicts aging phenotypes, diseases, and mortality. So first about the signature model training, we used data from the Framingham Heart Study offspring cohort with over 2,000 participants with mean age around 67. We estimated individual level longitudinal slopes from 3 objective measured frailty components: the weight, the grip strength, and the working time, which represent key physical domains of the frailty phenotype, and summarized them via principal component analysis. The first principal component will serve as our frailty pace signature. And then using plasma proteomics, that is over 2,000 proteins measured by the Olink platform at exam 8, we applied elastic net regression to identify a panel of 112 proteins predictive of frailty pace. We next evaluated the robustness of the proteomic frailty pace signature in external cohorts. The first was Framingham Gen 3, a younger cohort that represents the offspring of the Framingham offspring participants. While it is not fully independent, it provides an opportunity to validate the signature within the same community, but across generations with a substantially younger age distribution. We also validated these signatures in the UK Biobank, a large and independent population cohort, including more than 40,000 participants. And we examined the associations with age-related phenotypes and tested incident outcomes like mortality and chronic diseases using regression and Cox models, adjusting for demographic and lifestyle factors. A false discovery rate threshold of 0.05 was applied to account for multiple testing. And before jumping into the results, here is a quick look at the cohort characteristics. So our proteomic Friday PACE signature was trained on the Framingham offspring cohort and validated in Framingham Gen 3 and the UK Biobank. And we can see clear differences in the age range from the older adults in the offspring cohort to much younger participants in Gen 3 and UK Biobank, as well as the ethnic composition, with Framingham being predominantly white. This contrast allows us to evaluate both the within-study reproducibility and the external generalization of the proteomic Friday PACE signature. And now let's move into the results, and that is where the things get exciting. So first, we look at the associations between the proteomic Friday PACE and the age-related phenotypes in UK Biobank and Framingham Gen 3. Across the two validation cohorts, we observed that higher proteomic Friday PACE scores were consistently associated with poor physical performance, such as slow walking pace, poor self-reported health, higher BMI, tiredness, weaker grip strength, and worse lung function. And in the UK Biobank, higher Friday PACE scores were associated with reduced fluid intelligence and slower reaction time. In Framingham Gen 3, which is a younger cohort with fewer cases of cognitive impairment, we observe a similar but non-significant trend towards lower cognitive domain scores. And beyond the physical and the cognitive performance, across the validation cohorts, we also observe higher Friday PACE scores were linked with several biological markers of aging, such as higher CRP, shorter telomere length, lower albumin levels, and lower IGF-1. All these relationships appeared after adjusting for chronological age, sex, demographic, and lifestyle factors, suggesting that the proteomic signature captures something beyond just getting older. It reflects how fast individuals are biologically aging. And this slide is presenting that the proteomic Friday PACE signature predicts incident outcomes as well. So in the UK Biobank, participants with higher Friday PACE scores have higher risks of mortality and a broad range of diseases, including cardiometabolic, renal, hepatic, pulmonary, neurodegenerative, musculoskeletal, and cancer outcomes. And importantly, these associations remain strongly significant even after adjusting for the chronological age and other covariates. And so far, we have seen that the proteomic variety pace predicts a wide range of aging phenotypes, diseases, and mortality. So the next question is, are these associations consistent across different ancestry groups? To address this, we further examined the generalizability of our proteomic signature across ancestry groups in the UK Biobank. And here is the results. So we see here that the associations largely replicate across the white, Black, Asian, and mixed ancestry participants. Although some attenuation were expected due to smaller sample size in the non-white groups. And we show the results for the associations with the age-related phenotypes as well as the incident non-cancer diseases and mortality. For the incident cancer outcomes, we did not present the subgroup analysis here because many cancer types have too few cases among the non-white participants to yield stable estimates. So overall, the associations replicated well across diverse ancestries, supporting the robustness of our findings. But still, expanding to larger and more diverse cohorts would be beneficial for further confirming the generalizability of our proteomic variety pace signature. And lastly, let's take a more detailed look into the proteomics contributing to the variety pace signature. The 112 proteins contributing to the variety pace signature are enriched in multiple biological pathways, including muscle contraction, extracellular matrix interactions, immune responses and inflammation, metabolism, and neuron development. And the protein-protein interaction network analysis also confirms strong functional connectivity, suggesting that these proteins jointly capture the multi-system aging biology. To summarize, we developed and validated the first proteomic signature of variety pace, a dynamic biomarker that integrates longitudinal physical decline. And it strongly predicts age-related outcomes independent of the chronological age and is replicable across genetically diverse populations. Compared with existing static aging clocks, this approach offers a mechanistic, informative, and dynamic measure of biological aging that could inform personalized prevention and intervention strategies for healthy aging. And I'd like to thank the RISE program again for providing this platform for young investigators to share our work. And special thanks to my mentors, Cassie and Joanne. And thank you all for your attention. I look forward to the discussion.
Thank you. Let's move to the next talk now. Alessandra.
Yeah, sure. Okay. Do you see properly? Okay. Good morning, everyone, and thank you for inviting me in a RISE webinar. Today, I'm going to talk about multi-state models with intermittent observation scheme in the aging research field. First, a brief presentation of my outline. I will first introduce the topic and our new method that I will assess with a simulation study, and finally, I will conclude with some remarks. So multi-state models are used to analyze life history processes in which each individual is expected to occupy one of a finite number of states at any given point in time. In many chronic diseases, individuals are typically assessed at discrete time points, such as routine medical visits, making transition between states inferred from periodical observation. The data that arise from this intermittent observation of a continuous process are referred to as panel data and are affected by two sensory mechanisms. Interval censoring means that exact transition time remains unknown, but it is known to have occurred between consecutive assessments, while event censoring occurs when the disease status of an individual remains unknown due to dropout or death before diagnosis. Methods for handling multi-state models with panel data can be broadly categorized into two approaches. Classic multi-state models assume full knowledge of individual trajectories, and under this assumption, the likelihood can be decomposed into independent contributions for each transition, making the optimization process efficient. However, these methods may introduce estimation errors when applied to panel data. On the other side, we have multi-state models for interval sensor data that explicitly account for interval and event sensory, and they require the estimation process to solve Kolmogorov forward equation while maximizing the likelihood. And since for most forms of the generator matrix it doesn't exist a closed form solution, they require numerical integration techniques that make these approaches computationally intensive. For this reason, in the literature, these methods are mostly developed under Markovian assumption because taking into account the sojourn time into intermediate state would add extra complexities. We aim to bridge the gap into existing methods by implementing a novel one that is sensoring aware but avoids the burden computational burden associated to methods that are fully likely based. Moreover, in our implementation, we don't rely on Markovian assumption, and we overcome the need to reduce covariance patterns associated to subjects to ensure computational feasibility. Eventually, we conduct a simulation study to assess the performance alongside with other approaches under different exposure patterns. We focus on the development of dementia as a case study since it is well suited for representation within a irreversible illness-death process in which individuals transition from dementia-free state to dementia and then die, or directly die without developing disease. Moreover, as a chronic condition, dementia is monitored just at periodical assessments, making it a perfect example to study both interval and event censoring. I'm going to now propose our new method that is developed under illness-death model. And before delving into the details, I'm going to explain the core idea. So inspired by the paper of Yu et al., we decided to reconstruct the trajectories for each individual and treat them as exactly observed instead of accounting for probability of an observed transition. More specifically, in a first implementation, we developed multiple imputation for panel data, in which we relied over two Cox models, one for onset disease and one for death. We extract from them ad hoc quantities to impute and reconstruct multiple trajectories for each individual. Then, for each imputed dataset, we feed multi-state models, assuming exact observation time. And finally, we pull the estimates, accounting for uncertainty with the Rubin's rule. In a second phase, we moved from the model-based to the learning-based imputation in order to relax some assumptions, such as the proportional Cox hazard. And I'm going to now focus on these two phases of the imputation. So in those cohorts in which individuals are assessed at periodical times, some individuals develop dementia but are not, the disease status is not registered due to dropout or death before diagnosis. For this reason, we observed a label, a proxy label that here is indicated with letter L, that might be different from the true latent status indicated with white stars. And it's important to note that the two labels are coherent when dementia is observed, but when we don't observe it, we could have any kind of true latent status. Moreover, we decided to work under selected random assumption, letting the selection probability depend on a subset of the subject's covariate instead of assuming it was constant. And we used to estimate the true status expectation maximization algorithm that jointly estimates a classifier for the onset probability of dementia and a propensity function. Then we used the estimated probability of developing dementia as a prior for disease onset of the next step, and also to define a label subset that we're gonna use for semi-supervised learning. We used two copies of the same architecture that is represented by two conditional variational autoencoder. We see on the left the student, which is optimized and updated through supervised loss over labeled subjects, and then the teacher whose weights are updated with a smoothly moving average of the students' weights. The input is represented by the prior that has been previously computed in positive and label learning, and covariates associated to each patient. And then we had a Gaussian noise to account for the uncertainty of this prior. The students receive the noisy prior and the covariates and predicts for each patient a posterior probability of onset and a distribution for onset age. And his weights are then updated, while the teacher receive different views of the prior of each patient, predict these different onset probabilities, averages them, and accounts for uncertainty. Then an uncertainty gate and a pseudo labeler retain only those predictions that are highly confident, and we ask the student to match the prediction of the teacher over these confident unlabeled patients or in the consistency loss. In this way, we can also retain information from unlabeled samples. And finally, at inference time, we use the teacher weights to predict onset probability, onset age distribution for each patient, reconstruct the trajectories, and fit the multi-state models. Let's now focus on the results of the simulation study. So in our simulation study, we assume age as a time scale throughout all the process and use delayed entry into the study, accommodating that with left truncation. And we observe the patients every 3 years. We introduce one binary time invariant exposure and evaluated 5 different exposure effects, starting with no exposure effect on death, then assuming no effects on disease onset, and then exposure effects over all transition, but with different magnitude. And to span from low to high incidence of the dementia, we changed the slope of the baseline hazard over the first transition. We evaluated the 5 different methodologies, relying on some R implementations for them. And we started by a method that assumes exact observation times and Gompertz distribution as baseline. Then we turn on methods for interval sensor data, starting with MSM that usually assume time homogeneity and relaxed this assumption, introducing a time varying covariates that let us model a piecewise Gompertz, and then letting the hazards smoothly change with time with NHM package. And then we examine our methods for reconstructing trajectories. There are multiple imputation for panel data and streams. And we have evaluated different metrics. Here we benchmark these five methodologies in the I-rate scenario, and we can see in each panel the bias associated of the estimated exposure effects. Let's start by assuming no exposure on mortality, and we see that the performance of different methods accounting for censoring or not could be comparable. However, the method B, in which we have a misspecification of the baseline hazard, introduce a systematic bias over the exposure effect. While when the exposure is not related on the disease, we see that methods that reconstruct trajectories have more accuracy on transition to dementia, while method C, that resolves numerically the Kolmogorov equation, is really sensible to the initialization, so it's unreliable. Then when we have exposure on all transition, we see that the benefit of accounting or not for sensory mechanism depends on the magnitude of the effect. For example, here the performance can be compared, and we are in the scenario in which we have stronger exposure on death for disease-free subject. For this reason, we decided to evaluate also other metrics. And we can see that the power associated to recognize non-zero effects of the exposure effect is higher in those methods that reconstruct trajectories. While for what concerns the coverage, we see that for method D and E, coverage is really similar from the method that assume exact transition time. So from this simulation study, we can state several conclusions. We have observed that the modeling censoring mechanism reduces bias, especially when the exposure effect is unrelated with the disease, while the power arises for those methods that reconstruct trajectory, especially at high event rates. Streams particularly offers a scalable and stable, numerically stable and sensoring aware alternative to existing methods that doesn't require resolution of ordinary equations, doesn't require matrix inversions, scales with the number of data subjects and not with the patterns, and doesn't rely on the Markovian assumption for implementation. As a trade-off, it needs enough data for training, and it might be sensible to hyperparameter tuning. And finally, it's less interpretable than classical multi-state models. As future direction, we would like to showcase this scalability, so show that the complexity increases with the number of subjects, but not of the covariate patterns. We would like to integrate high-dimensional covariates, such as the embedding of medical images to enrich the latent representation of subjects, and use a sequence encoder for time-varying covariates, since it exploits longitudinal information. And eventually, we would move from beyond the reversible illness death model by introducing a reversible transition for recovery and a prediction ahead for death. Thank you all for your attention. I would like to thank also Davide Vetrano, Francesca Ieva, and especially my mentor, Caterina Gregorio.
Very good. Let's move now to the last presentation.
Thank you, Anna, and thank you, everyone. Can you see my slide? Okay, thank you. So, my name is Dipendra Thapa, and today I'm going to present some of the findings as well as the approach that we developed to test the effect of life-extending interventions on compression of morbidity. And I'm working with Dr. David Allison. This is my presentation outline. I would first briefly talk about the background on compression of morbidity. Then after, I'll describe a little bit about the issues related to existing studies on compression of morbidity, and then I will introduce our approach and methods. And then after, I will show the results of these methods in one of the data sets. And finally, I will give the concluding remarks. So, during the past few decades, we know that research has identified different types of interventions that can extend longevity, at least in model organisms, which includes caloric restriction, lifestyle modifications, epigenetic programmings, as well as pharmacological interventions. However, it is not clear whether these type of lifespan extending interventions improve health span relative to the extension in lifespan. So, or in other words, are people living longer also living in healthier? It's not clear. So, as longevity interventions on the one hand can compress the morbidity, and on the other hand, it can also extend the morbidity, which will be definitely undesirable. So, what is the relationship between increased lifespan and health span? There are three competing hypotheses. The first one says, yes, there is a relationship, and it's compression of morbidity. So the compression of morbidity suggests that the period of morbidity, which is sickness, could be compressed towards the end of life. So the onset of chronic diseases can progressively shift towards the end of the life, so which is higher, more rapidly than the improvement in life expectancy. So ultimately, people will spend lesser time in morbid state. And the other hypothesis, it says no, there is no compression of morbidity, and there is a famous paper called The Failure of Success, which says that medical advances would extend lifespan without improving health span. And there is the third one, which says that lifespan and health span could be extended in similar amounts, and there is a dynamic equilibrium between increase in lifespan and health span. So compression of morbidity, basically, it examines the relationship between the individuals who spend in healthy or vitality-free, disease-free state versus a morbid state relative to the total lifespan. So the period of ill health can be shortened, and it can be compressed toward the end of life. So ultimately, people will spend higher proportion of their life in healthy state. So ultimately, it will improve population health. So if you see this figure here, so there is the first row, you can see control, and the two rows, intervention A and intervention B. Although both intervention A and B are able to extend the lifespan, but intervention A also compresses morbidity. That is, it can push the onset of disease towards the end of life. There are two forms of morbidity compression. One, the onset of chronic condition rises faster than life expectancy, and the other one, the morbidity rates declines more rapidly than mortality rates. So what is the issues in existing studies which test the effect of life extending intervention on compression of morbidity? So basically, the existing studies examining compression of morbidity, they often analyze lifespan and health span as a separate entity, and they compare the p-values using different statistical models and thresholds. So I have presented here an example, a representative example of this study. This study tests the effect of alpha-ketoglutarate, these chemicals, on lifespan, health span, and compression of morbidity. So what they found is, on the one hand, this chemical, it improved lifespan. You can see the p-value 0.04. And on the other hand, it also reduced frailty index, so it's a form of morbidity. So based on these results, they concluded that by simultaneously reducing frailty and enhancing longevity, it results in compression of morbidity. So the problem here is it's a type of form of Dean's error, what we call difference in nominal significance. So significance between groups in survival and health span, it does not establish morbidity compression. The better test would be to incorporate both survival and health span in a single data set, and then after to compare those between the interventions group. This is a disjointed approach, which cannot readily say whether the intervention is causing compression of morbidity or not. So there is a lack of rigorous statistical techniques to test this hypothesis, and this lack of analytical methods has hindered the evaluating whether lifespan interventions also compress morbidity. So in short, there is no standard approach. Now I'll talk about our method. Before introducing our method for testing compression of morbidity, I'll give a brief background here. So we have this hypothetical graph, a typical curve plotting survival, the blue line, and health span, green line. So as population age, both mortality increases and morbidity also increases. That means survival and health span declines. Life extending intervention can improve late life survival. So you can see the blue dashed lines, which is shifted towards the right. So it's more rectangularization. So the survival has been improved. So how does that happen? Well, life extending intervention, it does so by slowing the rate of decline in survival. You can see at the age of 70 years, I have plotted the tangent of in that particular point, and you see the rate of decline, which is the slope of the tangent, is lower in the intervention group compared to the control. So we can say that this type of life extending intervention, this slows the rate of decline in survival. And the same thing can happen in case of health span. So in addition to prolonging lifespan, this type of intervention can also affect health span, and potentially it slows the rate of decline in health. So ultimately, we have 4 curves here, considering there are 2 parallel group designs, so 1 intervention and 1 control. And the key challenge here is how to analyze these 4 curves in an integrative way using statistically rigorous method. And we propose that the compression of morbidity hypothesis can be tested by comparing the rate of decline in health span to the rate of decline in survival towards the end of life. So we can calculate the difference between the rate of decline in health span and survival in control as well as the intervention group. And then after that difference scores can be compared between intervention and control, and that's how we can test compression of morbidity. So in our approach, we call it the difference in rate estimates Dyer method. So we define compression of morbidity as a situation where the rate of decline in health span, so we have referred to it as vitality, is slower than the rate of decline in survival. So this means the difference between these 2 rates, decline in vitality and decline in survival, would be negative. So in other words, vitality declines slower than the survival. Our hypothesis is that the difference between the rates of decline in vitality and survival is lower in the intervention group compared to the control group. So I have also presented here a hypothetical scenario for illustrative purpose. So here intervention, the difference between vitality rate and survival rate is lower in case of this green line, which is the intervention that compresses morbidity compared to the control. And if it's higher compared to the control, then in case of intervention B, it will expand the morbidity. So in our approach, this is the step-by approach in that we have developed. The first one is we will estimate the rate of decline in vitality, delta V, which is basically the first derivative of the vitality decline curve. Then after, we will estimate the rate of decline in survival at same points where we have estimated the rate of decline in vitality, which is the first derivative of survival curve. And then after, we'll calculate the difference between these 2 rates. And then we compare this difference between the intervention groups. So basically, this is the difference in difference analysis. And as I mentioned previously, the difference should be lower in the intervention group compared to the control, so that we can claim that the intervention compresses morbidity. And I'll present an application of this method in one data set. So we use this study by D. Francisco and others. They have tested the effect of dietary restriction on health span and lifespan in genetically diverse outbred made The sample size was 937 female mice. So they compared 5 randomly assigned groups. The control group, intermittent fasting at 1 day per week, intermittent fasting 2 consecutive days, 20% caloric restriction, and 40% caloric restriction. They started the intervention at 5 months. And they have measured this frailty index, which is a 31-item deficit scores. So baseline at 5 months and subsequently every 6 months. So altogether, we have total 6 measurement points. In our analysis, we converted the complement of frailty and calculated vitality, which is 1 minus frailty index, because we are considering here the positive aspect, health aspect of this one. So, and furthermore, for each subsequent time point, vitality was calculated as the proportion of the value recorded at the first measurement. So we give the value for first baseline measurement as 1, and then after each subsequent, we have calculated the proportion. This is basically just to standardize the baseline vitality across all mice. So, and then after we followed the same approach, first we fitted the exponential decay model for individual vitality trajectories, which is by this exponential decay model, V sub t, which is vitality at time t is equal to B sub 0, which is baseline vitality, which was set at 1. And this gamma is the exponential decay rate at time t. T is S, and C is the constant, which is the asymptotic vitality value. And then based from this equation, we calculate the average rate of vitality decline, which is the first derivative of this equation. And similarly, we estimated the rate of decline in survival by fitting Cox proportional hazard models. And from that model, we calculated the average rate of vitality decline. So I cannot directly calculate the rate of decline in survival from the existing softwares like StataR. So that's why this delta S, the average rate of vitality decline, has been calculated by differentiating the survival at particular point minus the previous point and divided by the time duration. And then after I calculate the difference between two declines, delta V minus delta S, and compared between the intervention groups by one-way ANOVA, Kruskal-Wallis test, and linear regression. And furthermore, the standard errors and p-value were obtained through bootstrapping with 1,000 resamples. So I'll present the results. Here I have plotted the raw data of vitality scores in left panel. So this is the vitality trajectories by intervention groups. You can see vitality declined more slowly in the intervention group compared to the control group. And the other one, this is the survival curve. All the intervention group exhibited, significant improvement in survival. And you can see the largest improvement can be observed in 40% caloric restriction group, followed by 20% caloric restrictions and others. So from this data, as explained previously, I calculated rate of change in vitality and rate of change in survival. So this is what it looks. So we calculated rate of change in vitality and rate of change in survival for each mouse at specific time points by intervention group. All these delta V and delta S were negative, signifying the decline in vitality and survival. I took the absolute value, and then after I calculated the difference, delta V minus delta S. So the ultimate aim is to compare this difference between the intervention group. And these are the results. So you can see what we found here is all the interventions group had larger score for difference between the rate of decline in vitality and survival. So you can see the mean difference here. So this is the larger in intervention because they are all negative. So this smaller negative value means larger. You can also see from here the linear regression compared to the control. All the interventions group had higher scores of that difference, with the difference significant in which one? This 20% caloric restriction and 40% caloric restriction. The same results I have plotted here. I have plotted the difference scores by the intervention diet group. So the black lines here, this is the lower compared to the intervention groups. So what we found here is the difference score is significantly higher in 20% caloric restriction and 40% caloric restriction group. So that suggests that this caloric restriction is contributing to expansion of morbidity, which is opposite to what we have hypothesized. And on the other hand, if you see this graph in left panel, you can see at certain age, the association looks like it's reversing. So somewhere at around 1150 days, so you can see the difference is lower in case of intervention. So at very old age, we also did a separate analysis to see whether the results differs for a very old age, but we found there is a difference, but which was not statistically significant. And one thing I want to emphasize.
1 minute, please.
Okay, I'm just this N refers to the number of measurement points of vitality and survival. It's not the number of mice. So there are some limitations of this study. I would not like to go through all of them. And in the future research, we aim to test or imply this methodology on the different distributions of mortality, as well as some of the other previous researchers that they have done and human observational studies. So basically, the method that we have proposed here, to our best knowledge, is it represents one of the first rigorous statistical method to examine compression of morbidity by incorporating both health span and lifespan. We found no evidence of morbidity compression as a result of this type of interventions. Instead, the evidence suggests that there is potential expansion of morbidity. So it challenges the assumption that the life expand intervention will compress morbidity. We do not claim that these type of lifespan extension interventions, it categorically fail to compress morbidity. Rather, we propose an innovative statistical method, and we believe that our method can serve as a default method for analyzing compression of morbidity. So I would like to acknowledge all of my, supervisors, co-authors. This paper has been accepted in Journal of Science, and probably it will be public in a couple of weeks. I would also like to thank all my co-authors. Thank you. And any questions, I'm happy to answer.
Yes. Thank you. All right, now we are going to open for questions. I would like to see if we have questions from the panel first. Still waiting for questions to be posted on the Q&A. I can't see any so far. Okay, I have Catherine back too. Any questions from mentors on other presentations? Otherwise, I have a couple here. All right, so my first question for Dr. Thapa. All right, so those are two separate models, right? And so you're doing steps, is what I understand, in stages, I would say. Alternatively, one could look at disability-free survival or, those other concepts. Did you think about doing that, or did you compare what the conclusion versus looking at, survival without disability, or, how that in comparison to the shrinking of that disability time of frailty, which you're calling the inverse, right? So their vitality is 1 minus frailty, right? That's my understanding. Yeah. Or would that be conceptually different? Because, that's when people really made it to, to a certain point without disability. Go ahead.
Thank you for the question. Great question. So basically, the way that you propose it has been used in some human observational studies. They use the concept of health expectancy. something similar to what you explained. So one of the problem with that approach is we have to make a certain cutoff score. So if you have this much, whatever the score for disability, you will be classified as disabled, otherwise no. So the arbitrary cutoff point, it can itself, it can introduce the bias over there. So that is one issue. But in our case, there is no need to make a cutoff point. We can calculate the rate of declines between survival and health span. So as I presented in one side, there are two types of methods. One is whether the onset of chronic illness or whatever the disability, whatever the conditions, when is that onset compared to the extension in lifespan. So the other one is how the morbidity and mortality decreases. So our approach is based on the second one, the larger one.
Thank you. Yeah, that makes sense. It'd be interesting to see how those complementary stories. All right, so mentors and no questions. I'll ask another question. No one can leave this panel without a question. All right, so Alessandra, that's a beautiful model, and I'm wondering if you could tell me practical example of application. What would be one real life application that we could use this model? Just a couple of examples that you're thinking about.
Yeah, sure. Thank you for the question. So basically, we have a lot of different chronic diseases that are modeled with multi-state models. So I chose dementia because I work a bit more on that and also in my department. But we could also evaluate other diseases such as diabetes or cardiometabolic diseases. These models are still valid. The only difference is in the exposure you want to apply on them. And we start on models that is, let's say, in this structure, it's easier because it's a illness death model. It has only free transition, but for sure we would like to reach this context to also expand it to reversible transition, because we know that it could be also diseases in which you can go back to the disease-free status. So that's a beginning, but we would like to work on also other diseases.
Very good, yeah. Because I think you can really apply to a lot of different, research questions. So thanks for explaining.
Yeah, this is why. Oh, sorry. No, I was saying this is why in the implementation we try to keep it some agnostic with a model assumption, because in this way it could be applied in different contexts. Thank you.
Yeah, it becomes easier to apply in practice, right? Because real data is not perfect, right? And so that's clever. We have a question in the chat. I think everybody can see. Let's see. This for Jiasheng. Okay. How did you model the frailty pace response variable? Was it a univariate variable or a multivariate response variable?
Yeah, thanks for the question. Definitely, there are various ways to do this, but for us, we are modeling this frailty component as multivariate responses with continuous variables for the three components that we utilize, which is the weight, the grip strength, and the working time. We coded them in, or we use a continuous quantitative version of these variables, and we capture their longitudinal trajectories across 3 exams in the Framingham Offspring data, and then extract their trajectory slopes to integrate them into a frailty pace score.
Very good. Stefan, let's see if that answer your question. You can post there for us. And still on you, I noticed that diabetes, there was a difference, right, by race when you show, the plot by condition. Did you explore that a little further, or it was just
Yeah, for the diabetes,
yeah.
so in UK Biobank, still the primary of those data from the white. So in that analysis, we are splitting to the subgroup of the white and the non-white. And as you mentioned, in the non-white group, we see that the type 2 diabetes associations for the hazard ratio is in a smaller effect size compared with the white group. So we think that so the association in the non-white for the signature with the type 2 diabetes is still significant under FDR 0.05, but the effect size is attenuated. We think it is due to fewer the smaller sample size of the non-whites and fewer cases in these non-white groups that we can make more generalized conclusions here. So we think it's important to utilize larger and more diverse cohorts. At least for the non-white, we expect to have a larger sample size to yield a more stable and a more convincing conclusion here.
Right, because there may be other things lurking out of race, right? That may be influencing. I'll get the last question, and then we are going to wrap up. I know we're past a little bit of time, but there is a question for Alessandra, wondering if you could add generative AI component to your DL model to address the lack of interpretability of the model.
Thank you for the question. So I talk about a lack of interpretability because I think it could be quite difficult for somebody that is not doesn't know the whole process to understand how we first process the data, how we use the generative model to impute the disease status and then to feed multi-state models. But actually, we already are using a generative AI component to make those predictions, and we don't lack interpretability on how this is made, but more about how the process works. So because it is not a complete pipeline, we use different algorithms and these different models to do different stuff. So maybe it's more difficult to understand the complete outline. But actually, if you go through each of them, they're kind of clear, I guess. Maybe not when you first see them.
Yeah. Right, and sometimes it's just a matter. I like to give these examples. Some models that are, sometimes the parameter specific doesn't have interpretation. There are a lot of situations like that when you're developing models. But then, like graphically, you can show it. So there are different ways you can help with interpretation. So, yeah. But
And also, if I can add, I think what
yeah,
is
sure, please.
really interpretable of the model is that in the last step, we actually fit the model using after the trajectory reconstruction, you can fit a classic multi-state model. So in the end, the interpretation of the final parameters that the research are usually interested in are still the one that we are used to see in any type of analysis. So I think this helps a lot for the interpretation. Yeah. So the black box part is just the initial part, but there is this last part that retain the interpretation, I think.
Makes sense. And I think we got a thumbs up, so I think we got it. All right. Thank you so much. With that, we are concluding the webinar and concluding the ARISE for the series. And now you're cooking the work, because this is a kind of little competition. Everybody that give presentations in the ARISE, they are finalists. We receive a lot of abstract. So you guys are the finalists. And so everybody will get a finalist certificate, and then we will announce in probably a month the top 3. Okay, thank you so much for your time and have a good day.
Thank you. Bye.
Thank you. Have a good day.